Let's see other graph problem. It is called graph value tree, and this is the medium level problem. We'll come and understand this problem, but before this, just I want you to go and see related video of this. So if you go to my channel here, you can go to the playlist, or you can search here graph, and you will see this course schedule. So first go and understand this problem, and then you can come back here, because the current problem is similar to this one. So this problem talks more about the directed graph, but here in this problem we talk about indirected graph. So in the directed graph, there is a edge from one node to another node, but this is the indirected graph. There is a edge from this node to here, and again edge from one to here. So this is indirected graph. Let's try to understand the problem. So problem says the graph value tree. So we want to know that if this graph is a valid tree or not. So the tree has node and they have the children, and this seems like a valid tree. But if you come here, this is not a valid tree. And why it is not valid tree, you can clearly see there is a loop. And if there is a loop, then that's not a valid tree. So that's the main condition is this. Other one, we can also check, like if this is a tree, then in that case you can observe one more thing. Like if you count the number of the vertex is a 1 2 3 4 5 here, and if you count the edge, then 1 2 3 4. So edge is always less than 1 than count of the vertex, and that is also a condition for valid tree. And if you see, this is the first conditions here. The edge is not equal to n minus 1. If it's not equal to n minus 1, because we know the edges should be exactly equal to n minus 1, then in that case it is not a valid tree. You can also check here. One thing is, this is the circle, there is a loop here, so that's anyway, based on the loop we know that okay, this is not a valid tree. But if you count the edge, see here, 1 2 3 4 5 vertex, and 1 2 3 4 5 edges and the vertex same, so that's also not the valid tree. So we know the edge should be 1 less than this count of vertex. Okay, so though we understand the problem, let's design the graph data structure. So when we design the graph data structure, in this case we know this is the key in a map. We put that in a key, this 0 as a key, and 1 to 3 as a values in an array. So for 0 key in an array, 1 to 3, and for the 1, again there is a edge from 1 to here. So for the 1 key, the value will be 0 and 4. For the 2 key, value will be 0. For 3, value will be 0. So in the previous videos, this video, we talked about a directed graph, and in the directed graph, this was the key, and the value will be 1 to 3. That's all. From 1 to 0, no direction, no edge. So the edge is from 0 to 1. So in the previous video, in a directed graph, the map, in a map we put the key value pair in that way. But in this time, this is in directed graph, so that's why the key will be 0 and the value will be 1 to 3. 1 will be again key and the value will be 4 and 0, and the 2 will be key and value will be 0. 3 will be key, value will be 0. So this way, I have written the code here. I'm iterating through this edges, and this edges has, this is one row, another row, third row, fourth row, and each row has 2 values. So I'm iterating through this array, and each iteration I will get one row, and at another one second row, third row, and from that I'm just getting the value v1 and v2. I have explained this thing clearly in the previous video. You can watch that also. And what I'm doing for I'm I'm creating the key, so the 0 will be key. So v1 is the key, and in the array I'm just putting the v2 here. If already exists, key already exists, like for first one, like let's say 0, the value will be 1, it comes here. And the second time when loop comes, this 0 key already exists, then we want to append, so that's here, we are appending here. So this is the logic about this 0 key, and these are the values. Second portion of if logic is this is logic is for this, like this time v2, like if say v2 I want to make key, and this one value. So for 1, this can be also value 0 and 4, because this is the indirected graph. So this is the additional logic compared to the previous one, because in the previous video we had the directed graph, so that's why we just put this logic, and this one is a new. But here you observe most of the code just I borrowed from the previous videos, so you'll find the similarities here. Okay, so till here we come here, and then we get the keys, and we created the the graph data structure. Let's see the graph data structure. So I'm going to debug this, and my debugger point is here, like let's say just put here also, and I run this, and we'll see our graph data structure, and which has the key 0, value will be 1 2 3, key 1, and value will be 0 and 4. We'll see that, and then again we'll come back. So I was supposed to debug. Okay, let's debug this. Debugger, here is our key. Okay, this time it ran, and our control is here, and by this time we have already prepared the graph data structure. And if you see the graph data structure, you can see 0 is the key, and 1 2 3, that was the below, that's the values. 1 is again key, that's a 0 4, 2 is a key, 0 3 0 4 1. So that's exactly what we talk for the 0 1 2 3, and for 1 0 and 4. So if you see for 1 0 and 4, right, and for the 2 0 3 0 4 4 1, so 2 0 3 0, and this 4 1. So we created this graph data structure here successfully. Now we'll talk about other logic. So in a previous video, what we found, when we did the DFS, and from the vertex we went inside this, like DFS search, and when we found a loop, then we said that okay, this is not the valid in a previous video, like we just say like there was a loop detected, so that's a different use case, but we added this logic in a previous video and just trying to find out there is a loop detected or not. So when we found this, like we went to the 0 1 and came back to 2, and then from here 2 again we went to the 0, so that means this time we found that okay, 0 is already visited, so that means we concluded okay, there is a loop. So come to the 0, went to the 1, went to the 2, and come back to the 0. So now we found the loop. So we did this thing in a previous video, and in this video also, in this problem also, we are going to find out the loop. But the challenge is here, if you do the DFS, from here you can come here, from the 0 you can come to the 1, come to the 2, come to the 3, so three places, but from 1 also you can go back to the 0. So if you can come back to here, based on our logic, if the node is visited, then we say there is a loop detected. But there is no loop here, because from the 0 we came to 1, and from 1 again we came to the 0, because there is a path from 0 to 1, 1 to 0. So in this case, that's a challenge. We need to find out how to solve this, because this is not a loop. This is just a indirected graph. So what we do in our logic, the next like when we start our DFS search from 0 and go to the 1, then it's fine. Okay, we can go to the 1, and from the 1 again, from 1, before going to the like the DFS, we find, like we try to find out in the children of this 1, and we know the children of 1 is 0, but we also know for the 1 the parent is 0. So if the parent is same, then we say that okay, this is not a loop, because from the 0 I go to this place, DFS, I'll come to this place, and for the 1, when I do the DFS, just from 0 I come here, and from here I know next thing is I'm going to the DFS, like DFS recursion. I can go here and I can go to the 0, but just think, like from 0 we just came to this place 1. Now next thing is we want to do the DFS on 0, but before that we want to check what is the children of this, and if we find the children 0 and we check that the children is also 0 and the parent is also 0, so in that case we say that okay, this is not the valid condition to find that loop detected. So that's the one extra logic. We'll do that. So let's see the code again. So till here we found the graph data structure. Now we got all the keys from there, like a previous videos. So we got the keys because through the keys we want to traverse, and then we want to do the DFS. I sorted this. I created a status, and a status is the size of vertex. And if you see on the top, this time I'm maintaining only 2 variables, not visited and the visited. But in the previous video that was a directed graph, and in that case I needed 3 variables, not visited and in a stack and visited. So I needed 3 variables for that, but for the in directed graph I just need 2 variables, not visited and visited, and this is just a value 0 and 2. That's a constant number. You can also compare directly with the 0, 2, but this makes sense, not non-visited or visited. So okay, anyway, so we got the keys here, and now we create the array, int array of the size of the vertex, and then from the keys we get the 0. So that's why we see that okay, 0 is not visited. Okay, so in a status we get the key 0, and we have the boolean this array. So in a status 0, of course there is a all false, false, false. Like let's say it is the vertex is 5, then a status size is 5. So in all the 5 indexes 0, 1, 2, all the indexes we have all the false. So I'm just saying that, checking here, okay, status v, and v is 1, because from the keys I'll just get 0. So 1 is not visited. Then just I'm trying to find out, has a cycle. There is a cycle, like if I start from here and go inside, is there any cycle anywhere? So I'm going to check that. I pass the graph status. This is very much similar to the previous video. Only thing is, I just pass 1, because for this 0 parent is 1. I mean parent is -1. There is no parent. So I'm just saying that okay, -1 is the parent. But if you find the cycle, then from here return false, because if there is a cycle, then that cannot be the valid tree. So I'm return false, otherwise return true. So in this way we'll get all the keys, and we'll start from there, and in that we'll make sure all the nodes are visited over there, and also there is no cycle. So main logic is in this hatch cycle. So this is the main thing where we have deal with this, and this is very small logic, but we need to understand very deeply this thing. Okay, so we started with 0, and that's why we came to this place, and we marked 0 as a visited. And for 0, this loop is giving me 3 children, 1 to 3 and 1 to 3. So before going to another DFS here, so another DFS logic is here, DFS. So before going to the DFS of this 1 and then 2 and 3, I want to know here, first thing is like the children. Through the loop we get the children 1, So first one, we check for one is visited. No, one is not visited. So one is not visited. We'll not check other condition here this time, but anyway, the one is not visited here. So if it is not visited, we'll come to this place, second condition. Okay, one is not visited. Yes, this is not visited. So this is not visited, that's the same condition. I'm just putting this condition is true here. So if it is not visited, then go and do the like cycle, like go to the DFS. From the one, start doing the DFS. So for the one, for this one, like from here we go and try to find out all the children. So from here again, this function is called again. We'll come back to this place, and this time we're passing the parent v, that is 0. So the parent is 0. For 1 we are passing the parent 0. So we'll come back here again, and then we know the parent is 0, and for 1 we are going to get all the values. So for 1 we get the 4 also, we get the 0 also. So before calling again another DFS level, we just check for these children 0 is a parent or not. First, 0 is visited or not. Okay, of course 0 is visited. And also we'll check it is the v1, that is 0, is a parent. So yeah, both is a parent. So I mean 0 is a parent, 0 is a child. So it's saying not a parent, then only true. So in that case, even though the this is visited, but we are not going to return true because this is not a cycle. So that's why you put this logic here. And in this way, we'll go to the each node, and we'll not find the cycle here, and we can return false. There is no cycle, so this is a valid tree. So let's do another dry run in this thing. So we'll start from the 0. 0 will be visited. Go to this one place, this one, and for 1 we have like 3 childrens, 1 2 3 4. These are the childrens, and from 1 we'll go to this place 2, and for 2 we know 1 is the parent. So from the 2 we'll go to the again 1, and we know that 1 is the child and 1 is the parent also. So in that way, even though 1 visited, it will not return true. So from 2 it will go to the 3, and again from the 3 it will go to the 2 and 1, and before going to the 2 and 1 children, will check what is the parent of this. So for here the parent is 2. I mean for 3, if you go here, so parent is 2, so will not, the child is also 2, parent is 2, so will not return. So this time we have not detected the circle. But from 3 to 1, if you go to the 3 to 1, so in this case, okay, 1 is visited, that's true. But if you see the parent, we'll check this one, visited true, but this is the v1 1, and not equal to parent. Yes, it's not equal to parent, because this time for the 3 the parent is 2. So for 3 parent is 2, and when we came here we found that okay, this is visited, and also parent is and child is not same. So in that case we can return true. That means we detected the loop here. So that's the whole logic here, and we'll see the Java solution, and then we are done. So same logic, I have maintained the 2 variables, not visited and visited, and then I check the conditions. If the age length not equal to n-1, if the age is not exactly equal to n-1, then return false. I created a graph data structure here, and then we call this logic here hatch cycle, and it's a similar concept here. And hatch cycle has the same logic, you can see. Yeah, so that's all for now. Thank you.